Our last topic here is using multi-lens instruments for magnification. You can create compound telescopes, compound microscopes, which are two lenses or more that have been put together in combination in order to magnify an object. So for a telescope, you use a combination of lenses to magnify very distant objects like a star or with binoculars like, a bird out in the field. A microscope is designed to magnify very close objects. So you have your two lenses here, and you put your object that you're trying to image, your little tiny object, super duper close to the what we call the objective lens. And then the combination of these two lenses together enlarges that image substantially so you can take a good look at like really tiny cells with your microscope. And we're going to work through a problem where we calculate the magnification of this entire microscope system. What happens in a microscope or a telescope is that the light will be refracted through our objective lens, the first lens the light moves through, and then it will form an intermediate image. And then that image serves as the object for the second lens. And with this as the object for my second lens, which is always the eyepiece of the telescope or microscope, then the image that we see from the second lens, which is the image we end up seeing with our eyes, is something that's much larger and much more magnified. So the strategy for these types of problems, for these compound microscope or telescope thin lens systems, is to calculate where the image appears for the first lens, use that image as the object for the second lens, and then you can find where the image was formed after that light was passed through the second lens. And you can use that in combination with the magnification for each lens in order to get the total magnification of the system. So that's the strategy we use to solve these problems, and we are going to work through one right now for a microscope.
Here I have my eyeball, a beautiful eyeball with lots of big, fabulous lashes here, and it's looking down the eyepiece of the microscope. The first lens that we encounter is what we call the eyepiece of the microscope. The second lens is what we call the objective of the microscope. We are going to calculate the magnification of this compound microscope. Compound microscope just means that there's more than one lens. Calculate the magnification of an object placed 6.22 meters from a compound microscope that has a 6 millimeter focal length objective and a 50 millimeter focal length eyepiece. The objective and the eyepiece are separated by 23 centimeters. The first thing we'll do is identify the knowns and our unknowns. So our unknown is the magnification of our system here. I'm going to label my lenses as objective is lens 1 and the eyepiece is lens 2 here, okay? So the focal length of my objective lens, which I'm calling lens 1, so I'm going to say f sub 1, the focal length of that one is 6 millimeters, okay? And then the focal length of my eyepiece here is 5 millimeters. I'm going to call that lens 2, so f2 is 50 millimeters. The objective and our eyepiece are separated by 23 centimeters, so I'm just going to draw that in here. So this distance separation is 23 centimeters. And we're told that we are magnifying an object that's placed 6.2 millimeters from our compound microscope. Well, with microscopes, the way it works is we're looking here through the eyepiece, we've got this other lens, and our specimen is going to be right here on the other side of the objective. Okay, so my objective has a focal length of 6 millimeters, so I'm just going to put it right here. I'm going to say that's the focal length of this lens, okay, 6 millimeters. My object is just ever so slightly beyond that. So my object is going to sit right here, okay? So this is my object. We are going to call this 6.22 millimeters D sub O1. That's 6.2 millimeters, okay? Well, what's going to happen for our problem is that we are going to use the thin lens equation for our first lens to figure out where the image will appear for our first lens. Then you use that image as the object for the second lens. Then you finally figure out where your final image is located. So we're going to have to use our thin lens equation twice, once for each lens. And the magnification of a compound system, that magnification is just going to be the multiplication of the magnification that we get of the object for the first lens times the magnification of the object that we get for the second lens. So we're going to have to find the magnification for each lens, multiply them together. In order to get the magnification, we have to learn something about the distance at which those images appear for each lens. Okay, so our first step then, once we've identified our knowns, we've kind of drawn a sketch of our problem, is to take our approach of using the thin lens equation for our first lens. So we know 1 over f is equal to 1 over dO plus 1 over di. We know f, we know dO. We're going to solve this equation for di so that we can get at the magnification. Okay. So I'm going to solve this for di, so I move this term 1 over dO to the other side. 1 over di equals 1 over f minus 1 over dO. So that's 1 over the focal length of my objective eyepiece is 6 millimeters minus 1 over the distance my object is, that's my specimen, away from my objective was 6.22 millimeters. Okay, so I take this, I take 1 over 6 minus 1 over 6.2, not 6.22, but 6.2, and then that gives me 1 over di. Once I get this number, I take the inverse of it to give me di. So then di is equal to, we go 1 over 6 minus 1 over 6.2, you get that number, and then you take the inverse of that to get di, the distance that our image is away from the first objective. So I'll call that d sub I1. And we find that that distance is going to be, our units here, we're in units of millimeters. So my answer is going to be units of millimeters. It's going to be 186 millimeters. Okay, so my image from my first lens here is going to appear at 186 millimeters or 18.6 centimeters on the opposite side of the lens. I've gone ahead and drawn that distance right here. So my image is going to appear somewhere here, 18.6 centimeters on the opposite side of the lens. Now, we learned from our discussion on thin lenses that if the object is located at a distance greater than the focal length away from the lens, which just barely it is here, then we have an inverted image. It's going to be upside down. So actually my image is going to appear right here and is kind of going to be upside down. So I'm not going to do the full ray tracing here. So this was O, I'll call it O1 as my original object. I1 is the image for my first lens. Now, for our second lens, the image from my first lens becomes the object for my second lens. So I1 is equal to O2. So this image right here becomes the object for my second lens for my eyepiece here. And now, using this as the object, I can figure out where the image should be for this eyepiece, which is going to be the final image that I actually see with my eyeballs. Then the next step is to apply the thin lens equation to my second lens, my eyepiece. I've got 1 over f equals 1 over dO plus 1 over di. I need to solve for di here. So we'll do the same thing that we did up here. 1 over di equals 1 over f minus 1 over DO. Okay, so the focal length of my second lens, my eyepiece, was 50 millimeters minus 1 over DO. What is the distance that my object is away from this second eyepiece? Remember that the image for our first lens now becomes the object for our second lens. We were told that there was this distance, 23 centimeters, between both of my lenses. This is the same thing as 230 millimeters, okay? And I already found that my image from the first lens, which is the object for my second lens, is located at a distance of 18.6 centimeters away from the first lens. So 18.6 centimeters is the same thing as 186 millimeters. So then to find the distance that my object is away from my second lens, I have to take 230 millimeters minus 186 centimeters to get this distance right here, which I will call that DO2. Okay, so maybe I'll say that over here. DO2 is equal to 230 millimeters minus 186 millimeters, and that equals 44 millimeters. So this object is 44 millimeters in front of my second eyepiece. So that's what I'm going to put here for DO, 44 millimeters. Okay, 1 over DI is equal to 1 over 50 minus 1 over 44. Take the inverse of that number. That gives me DI is equal to negative 367 millimeters. And that's also minus 36.7 centimeters. Our image, final image, is going to appear at 36.7 centimeters away from this eyepiece, and it's going to be on the same side of the lens as the object. So this minus sign means that the image is on the same side as object for our thin lenses. Okay, my image then is going to be over here, a distance of 367 millimeters from the second eyepiece. Okay, so my image is going to appear somewhere over here at 367 millimeters, which is 36.7 centimeters. I'm just going to put a dot right here and call it I2 for where my final image should be, which is the image that I see with my eyes when I look through this series of lenses. And we are going to determine how big this image is and whether it's upright or inverted compared to our original object. So how do we do that? Because really we wanted to solve for the magnification of our system. I didn't yet find the magnification of the image after it passed through each of the individual lenses. So we should do that now. And I'm going to do that right here, I guess. So we do that. M1, the magnification that we get for our first lens here, is going to equal minus DI over DO. The distance our image was away from the first lens was 186 millimeters. And then we're going to divide that by the distance our specimen is away from the objective lens, and that distance was our 6.22 millimeters. Okay, so we've got minus 186 divided by 6.22 millimeters gives me minus 30 for the magnification for the first lens. This minus sign for the magnification means that my image is going to be upside down compared to the object. So my image is going to be upside down here, and it's going to be 30 times larger than my original object. Okay, that's what microscopes do. They enlarge on things. So actually, this image, I drew it upside down already, but it's going to be much, much taller, right? This is not quite to scale, but it's going to be much, much bigger than my original object. To find the magnification for our second lens, or the eyepiece, we've got M2 equals minus DI over DO. For our second lens, we just calculated that that image appears at a distance of minus 367 millimeters away from the lens. Minus because it's on the same side of the lens as the object, okay? And then we're going to divide it by DO, the distance that our object was away from the lens. And remember, for our second eyepiece, the image for the first lens becomes the object of the second lens. So DO here we calculated to be 44 millimeters. We've got a minus times a minus, so that gives us a positive magnification of 8.34. That means that the image for our second lens, our eyepiece, is 8.34 times greater than the image created from our first lens, which is the lens that we called the objective. This positive sign means that the image that gets produced from my eyepiece here, my second lens, is going to be the same orientation as the object. So my image that I'm going to form way over here for my second lens is going to be the same orientation as the object was for my second lens. It was already upside down, so that means that my image here, my final image, is going to also be upside down. This is going to be upside down. Okay. Now we can find the total magnification of the system, which is going to be the magnification for my first lens times the magnification of my second, and that would be minus 30 times 8.34. That turns out to be about minus 250. Okay, so the total magnification that I can get with this microscope is 250. My image that I'm going to see with my eyes is going to be 250 times larger than my original object. This minus sign means that my image that I'm going to view with my eyes is going to be upside down compared to the object. And you might notice this when you're using microscopes, unless there's an additional mirror in there that helps to invert things. You're looking through the eyepiece at your specimen upside down. And this also happens sometimes in telescopes too. So here, my image is going to be upside down compared to my object, and it's going to be 250 times greater. So I'm not going to be able to draw that to scale, but over here, my image is going to be 36.7 centimeters away from my eyepiece on the same side as my specimen, and it's going to be upside down, and it's going to be larger by a factor of 250 compared to my original object. So this is what we have to do using our thin lens equations in order to figure out the magnification of multi-lens systems. The more lenses you put in here, the more of these processes you have to go through, and then your magnification for the total system becomes a multiplication of the magnification for each individual lens.